Newton's law of universal gravitation. Isaac Newton focused his attention on the motion of the moon about the Earth. The moon makes one revolution about the Earth in 27.3 days. The distance of the moon from the Earth is about 3.85 into 10 to the power 5 kilometers. Based on this data, Newton calculated the acceleration of the moon directed towards the Earth as 0.0027 meter per second square. Newton grasped the answer to this question by his famous observation of an apple falling from the tree on the Earth. This led him to the idea that the Earth attracts all bodies towards its center. He assumed that the laws of nature are the same not only for earthly bodies, but also for all other celestial bodies. He proposed that the force operating between the Earth and an apple, and that operating between the Earth and the moon, must be attractive in nature and governed by the same law. Newton also observed that it is not only the Earth which attracts other objects, but every object in the universe attracts every other object, and he termed such a general force as the force of gravitation or gravitational force. The law is known as the universal law of gravitation. According to this law, the gravitational force of attraction between any two bodies is directly proportional to the product of their masses, and inversely proportional to the square of the distance between them. If the masses of any two bodies are m1 and m2, and the separation between them is r, then the gravitational force of attraction between them is F, is proportional to m1, m2, by r square, or F is equal to G into m1, m2, by r square, where G is the proportionality constant, and is called universal gravitational constant. Every body in the universe attracts every other body with a force which is directly proportional to the product of their masses, and inversely proportional to the square of the distance between them. The force acts along the line joining the two bodies.
Newton's law of universal gravitation states that any two bodies exert a force on each other that is proportional to the product of their masses and inversely proportional to the square of their distance apart. The constant of proportionality is known as the gravitational constant g, and its value can be determined experimentally. It is called a universal constant because it has the same value irrespective of the properties of the interacting bodies. Used together with Newton's second law of motion, F equals ma, Newton's law of universal gravitation enables the calculation of the trajectories of bodies under gravitational forces, including the orbits of planets around the Sun. To understand Newton's law of universal gravitation and its implications, let us simulate the motion of two masses under their mutual gravitational forces. The ratio of the two masses shown here can be varied using this slider. Now the mass ratio is 1, so that the two bodies have the same mass. And now the ratio of the two masses is 100. The yellow arrows denote the gravitational forces exerted by each body on the other. Note that they are always equal and opposite, even when the masses are different, in accordance with Newton's third law of motion. The forces act along the line joining the centers of the two masses. Let us change the ratio of the masses back to 1. Once we click the Start button, the two masses will start moving under the influence of the mutual gravitational forces given by Newton's law of universal gravitation. They will move because Newton's second law of motion, F equals ma, implies that if you have a resultant force F acting on a body of mass m, then it produces an acceleration given by F over m. Let us see this in action now. As you can see, the two bodies are starting to move. The green arrows denote their velocities. The white marks indicate their positions after successive equal intervals of time. The fact that the marks become more widely spaced demonstrates that the two bodies accelerate. Note that the acceleration is not constant because the force increases as the two bodies get closer, in accordance with the inverse square law of gravitation. Let us now change the mass ratio to 50 and restart the simulation. Although both bodies experience the same force, the one with smaller mass experiences a much larger acceleration and therefore moves faster than the larger one. As an example, an apple falling from a tree due to the force of gravity of the Earth also pulls Earth with the same force, but because the mass of Earth is so much larger than that of the apple, Earth moves a negligible distance compared to the distance through which the apple falls. Let us now look at the application of Newton's law of universal gravitation to planetary orbits. This simulation calculates the orbit of a planet approximately the size of Earth around the Sun. For simplicity, the motion of the Sun is neglected. This is justified because the mass of the Sun is more than 330,000 times that of Earth. As you can see, the orbit of the planet around the Sun is elliptical. Different shapes of elliptical orbits are possible by changing the initial speed and angle of the planet. For example, changing the speed to 35 gives a more elongated ellipse. and if we change the angle to 50 degrees, it gives an orbit that looks like that of a comet. All these orbits are calculated using Newton's law of gravitation together with Newton's second law of motion, F equals ma. This illustrates the predictive power of Newton's law of universal gravitation.